Okay, so what I want to do in this video is talk about motion and how does calculus, how is it related to motion, right? One of the most obvious application of derivatives and integrals, which we'll learn later, is motion, because it's so easy to see and understand. So we should get a good foundation of position, velocity, acceleration, how they're all interrelated to each other. But we're just going to be focusing on defining the terms. So here we go. Position is just a location, right? It's just a location. For the purposes of math and physics, it's typically on a number line. So you can think of it as a two-dimensional graph, right? Where this axis is time and this is your position. You usually like to say S. So what would something like this graph look like? If I were just to do a straight line going forever, what do you think that looks like? Let's say I'm here, right? Let's say this is where I am. I'm at position. Let's say this is my reference point, and I'm just 1 meter away from it, right? I want to be. This is like a flag, I guess. I'm 1 meter away from this, and the flag. How do I change over time? Right? How am I changing? Am I staying in place? Am I moving? It doesn't seem like I'm moving, because it seems like I'm always 1 meter away from the flag at always. Right? What happens, I'm going to do it in blue, if I start here and I slowly get here, like this. So it's a straight line, just imagine that. So let's say this is my reference point, right? So I'm going to put a flag. I start here. Right? Start here. The reference point. Let's say this is time t equals 1 and this is t equals 2. How does my position change as time passes? Well, at 1 second I am 1, so just pretend this is like another snapshot of me. I am 1 meter away, right? 2 seconds later, or 1 second later after that, which is 2 seconds total, I am 2 meters away, right? So this is a total distance of 2 meters. That's the idea of position. We want to track how far we are from a reference point, and usually the reference point in math is the origin, or you can picture like a landmark that you're trying to measure the distance you are from it. And position are important because we can actually make it in terms of a function, right? So this blue line, it actually is a function. It is defined as 1/2 t, right? So whatever t is, I'm just half of it. So let's see if that's true. So this is like halfway here, right? Halfway, this is about 0.5 meters, and this is 1, right? See what happens when we plug in t equals 1. T equals 1, I'm just 1/2, that is 0.5, right? And a unit would be good to have, so meters. If I'm 2 seconds into the position function, I'm at the location 1 meter, right? So that's the idea of position. The next two terms I want to look at are displacement and distance, and they're kind of weird in a way, because they're kind of describing the same thing, but they're subtly different. Subtle. It's very subtle. What I want to do is look at this. Let's say I start here, right? Like on a map. Pretend I'm on a map, and I want to get from here to here. Maybe the path I might take looks something like this. Let's say I have to go around something here. I'm almost there, but then I have to turn around here, and then I end up at my position here. What the displacement is what it is. It's what here. Oops, not that. That's a bad line. Let's do a better line. This is a better line. This is what the displacement is. What is your change in your position? So first I was here, and now I'm here, right? What is the distance? The distance is actually this purple line. So this is the distance. So let's see. This is the distance, the whole path I took. It's the total length. All the detours are included. The displacement, oops, I forgot a t here. The displacement is just where did I start and where did I end. We don't care about what happens in between. So try to keep this in mind, because when in problems you'll see the word distance, you have to think of distance like this, the long path. With displacement, you have to think of that path only about the positions. So how do we even track positions? Another quantity we want to look at is something called velocity. So we're moving up. Velocity, you can think of it as the change in position as time passes, right? Time passes. What I mean by that is that we want to track what the change, the delta x, though with delta s in this case, because it's position, delta s, as time passes. So we want to divide it by the change in time. This is what the definition of velocity, the average velocity, because it's not at a specific point, right? We want to look at specific points, and the only way to do that is through calculus. So what happens when we take the limit as t approaches 0 of this? Well, if we do that, it kind of looks like it will end up being something like this. So t plus h minus s of t all over h, I should say h. And this kind of looks like the definition of the derivative. And what this is equal to is it's instantaneous. So I'll put instantaneous velocity. What I'm trying to get at here is, if I just scroll down a little bit, just a little bit, what I'm trying to get at is this. The position function, if you take its derivative, it's equal to the velocity function. Okay. Now, another quantity that gets people confused is speed. Speed is kind of like velocity, but not really at the same time. Kind of like distance and displacement. There's subtle differences between them. So, when I'm talking about velocity, right, I'm talking about it needs to have like a size and a direction. We call that in physics a vector, but for the purposes of a calculus class, we're only going to be focusing on direction as positive and negative, right? So I can be going this way 3 meters per second, right? The positive direction, or I can be going this way minus 3 meters per second. This is a velocity. The speed doesn't care about what direction you're going to. It only tells you, it only wants to know how fast are you going. It doesn't matter about the sign. So even though this is -3, the speed is still 3 meters per second. No matter what, even if it's positive, if it's negative, it's always going to be the positive version. And when I think of positive version, I think of the absolute value. So how are speed and velocity related? Well, the velocity vector, if you take the absolute value of it, it's equal to the speed. Right? Or if you want to do it more, if you want to do it like in terms of position, you would say speed is equal to, so it's equal to this, right? Which is also equal to the absolute value, the derivative with respect to time of the position function. And this is really important to know, the difference between velocity and speed. And then the final quantity, oops, let me scroll down a little bit more. There we go. Final quantity is acceleration. Acceleration is just simply, we can go through the long explanation of it, but it's just, in short terms, it's just the derivative of the velocity function with respect to time. What does this even mean, right? Because acceleration is a kind of a weird concept. Its units are usually in like meters and seconds, is meters per second squared, but what does that really mean? It doesn't make any sense to a lot of people. Let's say I have a box, right? This is a box, and this is the ground. Let's say the acceleration is going down. Alright, let's say vertical direction, this is up and this is down. So down is negative. Let's say it's -1 meters per second. Let's say I drop it at v equals 0 meters per second. Right? Let me write this over here. A equals -1 meter per second squared. What happens at t equals 1? I'm going to draw a dotted box right here. What is its speed? At t equals 1. Time equals 1. Well, since the acceleration is -1, it should be going down. Oops, I don't want the rainbow color. v equals -1 meters per second. What happens at t equals 2? So here's the box again. Well, it has to keep increasing velocity. So its velocity is -2 meters per second now. And then we keep this going. T equals 3. Trying to draw it lower and lower. This time the velocity should be -1 more meter per second. What I'm trying to get at here is saying that the acceleration measures how much the velocity is changing every second. That's why it's per second. A way to keep this in mind is saying, instead of saying meters per second squared, you can say meters per second. So it's changing 1 meter per second. Every second, the velocity is changing. I'll say it again. Every second, the velocity is changing by 1 meter per second. So at t equals 5, it should be at -5. Let's do just one more thing related to acceleration. Just another visual thing. Let's say I have a box car, for example. Let's say it's driving at 2 meters per second, and the acceleration is 3 meters per second. So I want to just start tracking its motion. So at t equals 0, we know that it's traveling at 2 meters per second. What happens at t equals 1? Remember, every second it's increasing the velocity by the acceleration. So that means it should be 2 plus 3 meters per second, or 5 meters per second, right? At t equals 2, it should keep increasing its velocity. So that's 8 meters per second, right? Every second it's increasing by 3 meters per second. And so on. Right? So then we get 11, right? And these are all in seconds. Let's do that same example, but with a different acceleration value. Let's say this is a super fast box car going at 20 meters per second. And the acceleration is actually -4 meters per second squared. Let's track its motion. T equals 0. Let's move it down. T equals 0 is traveling at 20 meters per second. T equals 1. So now it's changing velocity in the negative direction, so we have to subtract, right? Every second the velocity is changing by 4 meters per second in the opposite direction, so it's 6 meters per second. T equals 2. Again, we have to change the velocity. As a change in velocity happens, it's -4, so it's 12 meters per second. And then keep this pattern going and we'd get 8 meters per second. So think of acceleration as how much is the velocity is changing every second. If you want a good visual intuition, think about this kind of example, like a car driving and acceleration, or a box falling from the sky. And then how are everything related? I told you, remember? The acceleration function is equal to the derivative of the velocity function. And then how does this relate to position? It is the double, or the second derivative of the position function. And then next video we'll be looking at some examples of how to use any of these relationships, or even this relationship. Oops, it's not this one, it's this one. There we go. Or this relationship. We'll look at examples involving these types of relationships, see how to actually do it mathematically instead of intuitively.